This is my second example. It will again be based on our earlier computations. That effort we did, you see, I'm making sure it's not wasted. We're just reusing and reusing that effort, which is good. There was another matrix 2 days ago, this matrix. 1 on 5, 1, 0, 2, 0, 0, 0, 2, 0, 4. For these metrics, we also have done the diagonalization. We found that the matrix is diagonalizable. As a matter of fact, if you remember, that was the matrix of projection map. And for that matrix, we did the spectral analysis. So we found a diagonalization 2 days ago for this matrix. And the pair of P and G, for this matrix, it was like this. G was the diagonal with the entries 1, 0, 0. That was the choice of G, which worked. And P, it was like this. It was 1, negative 2, 0, 0, 0, 1, 2, 1, and 0. That was the choice of P. That was the choice of P. Actually, 2 days ago, we also computed the inverse of P. And I copied that from 2 days ago slide just for completeness purposes. As a matter of fact, for the computations I'm about to show you, this P inverse, it's not necessary. But anyway, that was the choice of P inverse. That was the result for the P inverse we computed with you 2 days ago. If I'd like to find the power of my A matrix, this A matrix, we know that's the formula. So all I have to do, I have to sub in my pair P and G into this formula. But the good thing is this, look at this. If you compute the k power of the D matrix, you have to raise diagonal entries to the kth power. But the diagonal entries, they are such, it's 1 and 0. If you take them to the kth power, they will be 1 and 0 again. There won't be any changes. It's an interesting problem. Remember, we established this for the projection maps, and that was the matrix of a projection map, if you remember. In case of projection maps, eigenvalues are always 1 or 0. Meaning that if I take the D to the power k, it will be still D. So as a matter of fact, this one is simply PG, P inverse, because D to the power k is D. Am I right? And that is A, which tells me that the power of this matrix is just A itself all the time. There's a minor discrepancy in what I said. Can you spot that? When you compute 0 to the power 0, what's the value of that? Well, convention, we just make a convention, it is 1. So as a matter of fact, what I said will be true when I add this extra line. This is true for k integer, and you see I even made a typo. Strictly bigger than 0. As a matter of fact, I should say n here. That's a better name. And this can go. So every positive integer power of A is simply matrix A again. 0 power obviously will be identity, and we don't have the negative powers because you see my matrix possesses 0 eigenvalues, which is a sign of being not invertible. There's no any inverse. That's why there's no point computing the inverse powers, the negative powers of the matrix A. And that's all there is to it. You see, we didn't even need this representation, this P inverse for my computation.